A very good evening to one and all. Welcome to day two, third technical session of 6-day online faculty development program on recent advancement in e-mobility for developing power utility, sponsored by AICTE ATAL. Resource person of this technical session is Dr. Dhiman Das. On behalf of our organizing team, I welcome you, sir, in our today's technical session. Before you start your expert lecture, I would like to share a short biography of you to the participants. Dr. Das received the master's degree in industrial electronics from NIT Rourkela and PhD degree from IIT Delhi in 2016 and 2022 respectively. After his PhD, he was in IIT Kharagpur as a senior research fellow for 6 months. Then he had joined Tata Elxsi in India as hardware specialist. Currently, he is working as senior power electronics engineer at Huawei Technology in Sweden. He has authored and co-authored in various research papers in international journals and conferences, which including some renowned IEEE journal, transaction, his paper award, best paper in IEEE Second International Conference on Sustainable Energy and Future Electric Transportation in 2022. Also, he has authored in different Indian patents. Most of them are already granted. Dr. Das has research experience in area of power electronics and also has industrial experience as an R&D engineer as product development. His research interest includes DC-DC converter designs, multi-level inverters, renewable energy harvesting system, charger for electric vehicle application, EMI, EMC, digital embedded control, PCB design, non-linear control of switched mode power supplies. With this, I would request our expert, Dr. Dhiman Das sir, kindly enlighten us with his words of wisdom. Sir, please.
Thank you, Archana. Thank you all for inviting me for this lecture. So, should I start?
Yes,
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 sir.
yes.
Yeah, thank you very much. So, today I'm going to present some advanced active gate driver, which is a recent trend in power electronics with those EV charger and all the power electronic device need a suitable gate driver because nowadays new device came up and like silicon carbide MOSFET and normal silicon device also. So for that, a suitable gate driver is required. So for that, what are the criteria for driving the gate of the MOSFET or the MOSFET driving? What are the protection is required? We will discuss in this lecture. So let's start with basic recent switches which are available in the industry. So the common one is the silicon MOSFET. This is the basic switch which is used in which is mostly used in the all of the converter. But the problem of this silicon MOSFET is that the voltage limitation is the 650 volt only. Now we move to silicon IGBT, which is operate more than 650 volt condition. But the thing is that the operating frequency, this is quite slow device. So the operating frequency is limited to 20 kilohertz only. but it is very much useful for motor driving application. But nowadays, we are concentrating on very compact device, so high density power device. For those thing, we need a high speed transition and high speed switching action. So for that, uh, IGBT is almost getting obsolete. Now, this silicon carbide device is capable of handling high voltage. The maximum voltage available is 1700 volt, 1.7 kV, and it also have low RDS on, means uh, the turn on resistance is very low. Also, due to the high speed electron mobility, it can operate at very much high frequency. This is just basic introduction of the switches. Now, I would like to just for brainstorming, uh, all are this is a TO247 package of a switch. This is very much popular package. Now, uh, yes. Now, if anybody give this switch to you, how do you identify which kind of switch it is? Like it can be a BJT by normal transistor. It can be a MOSFET. It can be IGBT. So why a suitable gate driver is required for different switches? Anybody can share his idea about it? Anybody? How do you identify a switch from this black box kind of thing? Because every switch has a three terminal. One is input terminal, and the rest two is output terminal.
Sir, NPN
Hello.
and PN.
Mm-hmm.
NPN and PNP.
All of the switches are NPN type, or N channel type. So you got a switch like a black box. Now, how do you identify which kind of switch it is? You can use any laboratory tools. Uh, you can drive the switch. You
We
don't
can
know the
use the multimeter. We can
okay.
use the multimeter and we will check continuity. If middle one, suppose conductor size will be connected to the hole, it will be the collector. Because area
Then
is more, collector area is more compared to others.
how do you identify, distinguish between BJT and IGBT? Both out collector are same, right? Okay. So start with the basic power transistor. So here the driving is very much important. So why the MOSFET is introduced over the transistor? So in transistor, the input base is current driven, and output collector current is some gain of the input current, right? Which is called beta, right? So for power transistor, beta is around 10 to 15, like 3055 transistor or something, power transistor. The beta is around 10 to 12. So if I want to extract from collector to emitter around 100 ampere, I need to drive at the base 10 ampere. So if I give a 10 ampere base current, then my amplification will be 100 ampere, right? This is called the beta, the current amplification factor. Now to drive the base at 10 ampere, I need a power supply of around 10 volt at least to drive this gate. So here at the input or at the base side, I am wasting 10 into 10, almost 100 watt for driving the input only. Hello? Anybody have any question? Oops, I cannot see this. Okay. So, so your efficiency of driving this transistor is become very much low if you see the overall efficiency, because most of my power is wasting to drive this to turn on the channel of this switch only. Now this overcome when the MOSFET is introduced. At MOSFET, the gate is voltage driven, and the output current, which is ID, drain current, which is flowing from drain to source, is not a function of the gate current. So this driver, from this point of view, I am gaining lot of energy to drive the gate of the MOSFET compared to when I driving the base of the transistor. Lot of power is wasting across the base. Now this is similar to your like what is my overall efficiency is depend on the how much current I am transferring from input to the output, from source to the load. Now this driving is actually just my waste of energy to operate the system only. So if I minimize the driving capability or the driving power, then my overall efficiency will improve. Are you agree? Hello?
Yes, right, sir.
Yeah. So now, to combine both this, both taking the advantage of driving the gate and this channel, the IGBT is introduced, where the gate is not a function of base current. This is just an voltage driven at the gate, and but the output current is depend on the collector to emitter configuration, which is like normal. The output is not like a transistor only, but instead of base, the gate is introduced. This is just an hybridization of MOSFET at uh, MOSFET at the input and BJT at the output. Now, due to the BJT at the output, the unidirectional current will flow from the collector to emitter only. But in case of MOSFET, this is just an resistance. When it is turned on, from drain to source, it forms just an resistance. Not, it is just turned on the channel. So it can, since it's a resistance, ideally it should conduct in both direction. The current can conduct in both direction, but in case of IGBT, this is one direction. This is the fundamental difference of switches and drives. Now, there is a little bit advanced silicon carbide MOSFET is introduced recently. Now,
Sir,
normal
my
silicon.
question is that, please, sir, my question is that after showing this, suppose you have given to me BJT, MOSFET and IGBT, then which instrument we are going to use to find out which is drain, source or terminal of this IGBT? After giving this, if you are giving one IGBT
is
to me. How we will driven means we have to apply the voltage and all the things, and that will be
yes.
we have to perform in the laboratory. We have to give the supply, and then again we will find it is IG base, it is collector, it is emitter. Basically, if somebody I have given to somebody some transistor and IGBT, and I am asking how which is the drain, which is the source directly. Is there any instrument which can identify?
Generally, these are the standard package, industrial package for any kind of switching device. So here, this terminal is gate, then is drain, or this drain is connected to tab for thermal dissipation, and then is source. This is one kind of configuration. This is standard configuration.
Okay, okay.
This is
GD,
all,
GDS.
sorry,
Okay. GDS, get and then
gate,
drain
drain,
and
and
then
source.
source.
Okay.
GDS.
Now coming,
Okay.
yes, now coming to this package, this is another package, same with TO247 package, but the thing is that here it is a quite different package from the quite different pin configuration compared to TO247. Here this is drain, this is source, and these two are power terminal, and this is source and this is gate. These are the signal terminal. I will discuss this in detail later on.
Okay, okay,
But
sir.
but this can be a MOSFET, this can be IGBT, not BJT. BJT is quite low, but this can be a IGBT, this can be a MOSFET. Now, how do you identify? Because of these characteristics, and why it is why gate driver is required to pump sufficient current at the gate or at the base, so that uh, the device can operate at its optimum condition.
Okay, sir.
Now, yes, thank you. Now this is the basic difference between silicon and silicon carbide. You can find it anywhere. There is nothing new. Just for sake of showing this, this is the silicon MOSFET is maximum operating voltage is 650 volt, which is standard. Somewhere 800 or 900 is a special case, but 1200 volt silicon MOSFET, silicon carbide MOSFET is standard compared to silicon MOSFET. Now you can see there is almost 2 times voltage stress you can give at the silicon across the silicon MOSFET having same package. Why? Because the band gap energy is more in silicon carbide technology. And also because of this saturation velocity, electron mobility, you can have lower RDS on compared to silicon. Obviously, you have to pay more cost compared to silicon because nothing is free. You have to. There is some cost to performance criteria. And also in special case, 1.7 kV devices are available. Okay, now we come to gate driver. So the gate driver can be classified with isolated and non-isolated because depending on the application. If your converter is non-isolated converter like conventional boost converter, then you can choose non-isolated driver, which is low side driver. If your converter is buck converter, then you have to choose high side driver. If your converter is fully synchronous synchronous rectification converter or having a half bridge configuration, then you have to choose half bridge driver. We'll discuss everything later in later slide. But if you're okay, so now it depends on how your control and how your power stage is interacting with each other, and what is the voltage level, what is the power level. If it is more high voltage, then there is a concept called common mode transient immunity. If this there is a barrier, okay, there is a common mode current from the power which can flow from the power stage to your control signal. Now, to avoid that, we need an isolated gate driver. Also, for automotive application, the isolation is must between a power stage and your control stage. So for that, very much required. So there are few popular is optical isolated, which is called optocoupler. Then flux isolated, flux coupled, which is like acting like a transformer. And another is capacitive isolation, which is CMOS isolation. Now, this is the internal of optocoupler. So where this there is one LED. When you excite this LED, light is transmitted to a photodetector, and from there the output is energized. The output can sense there's something input is given at the LED, and it can send some signal to the gate. Now the thing is that there, because the whole thing is integrated in a single package, so there is one capacitor coupling at the anode as well as cathode. So because of the transient current, so because of the common mode current of the transition, some current can flow and influence this LED. So this LED can either can be false trigger, either turn off or can be turned on, which is not as per your desire. Now, also the propagation delay is more compared to the CMOS isolation, which is the CMOS isolation is a kind of capacitive isolation. Here you can see this propagation delay is very much less compared to this optocoupler. So if, what is your switching frequency? Based on that your switching frequency, you have to choose your gate driver. And what is your exact application? Another is RF based isolation. The input signal is given through a RF modulator, and this RF modulator produce on-off keying modulation, which is majorly known as OOK oscillation, on-off keying, OOK oscillation, which is when input signal is given, it is first turn on, turn off. This is just like one single bit transmission. So when the bit is not transmitted, it considered that input signal is not there, so the output will not reflected at the gate. This provide better immunity at magnetic field. And since this RF oscillator, this is just an base oscillator, so it consumes low power compared to LED. So this is also low power. The consumption of consumption of power is very low compared to LED or or compared to any optocoupler. Okay, now whatever switches we saw in the in the book, this is just these switches only, but in practical there is a lot of parasitics across the switch. So first parasitics is the capacitor across the gate to source. This is the one of the major major capacitor or called input capacitor. That determine the speed of the device, because wherever your parasitics are, it can slow down your signal. Now another important parasitic is output capacitor. You may see in some data sheet this is written COSS, output capacitor, which is combination of drain and drain to source and gate to drain. And also this is just an lead. The actual MOSFET is inside the package, so there must be some inductance across the lead. So these are parasitic inductance across the lead, and also there is some parasitic inductance across the gate, but this inductance is not too much dominating because low current is flowing to the gate. But this inductance is too much dominating when high current is flowing from drain to source. That current is also pulsating current, not continuous current. So when the current transition from 0 to high amplitude happen, those inductor come into picture. Okay. Now, if any kind of switch have this kind of behavior, one is linear region. When you turn on the switch, it goes through a linear region to saturation region or switching region. For understanding, if this kind of switch you have seen in the laboratory, so every switch has one input and one output. So here, if I consider this lever as the input of the switch, and these two terminal is output of the switch, because from here to here current will flow. Now, when you shift the lever from one side to another, now just imagine the lever is just touching the tip of the conductor. So when this lever is just touching the tip of the conductor, the current will start to flow. But the resistance is, or the contact resistance is not optimum, right? Or not minimum. And also you can push more to downwards. That is your mechanical input. Are you agree? Hello? Okay. So similar kind of phenomena we can see in case of MOSFET also. So after a so that is called RDS on, because here it is locked. Okay. Now we can use that analogy to driving a MOSFET. So while you are driving a MOSFET, so you have to charge your voltage across the gate, which is VGS, from 0 to this VDD of your gate driver. So now inside the gate driver, this is just a buffer, right? So every buffer had some output impedance. So this is the internal impedance of the gate driver. This one you can find in the datasheet of the gate driver. They provide how much is the output resistance. Now you have to give some gate resistance just to control. Okay, so this is the output of the buffer is voltage, and here this is a uncharged capacitor. So when you connect a voltage source to a capacitor, the capacitor is initially short circuited, right? A discharge capacitor is short circuited. So now when you apply any kind of voltage to a discharge capacitor, a huge will flow to charge the capacitor, right? And this is the, now you want to, when a huge amount of current will flow from this buffer may get damaged. Now to control this injection of current, we need a resistor to limit the current. The current will be V by R. This supply voltage divided by the chain of resistance, that will be the maximum current that can charge to the capacitor, maximum induced current. Okay, so now every MOSFET also has a certain input resistance. This is like 1 ohm, 2 ohms, in the range of 1 to 2 ohms. Now this resistance is also specified in the datasheet of the MOSFET. Okay, now when you just apply one pulse here from your control signal, the output of the gate driver will see this pulse and initiate a voltage from 0 to VDD. In most of the case, this VDD is 20 volt in case of MOSFET. So this so across the gate, so this is okay. So if you see this picture, this is the VGS. So voltage is applied from minus. Okay, so you can at off condition, either the output of the gate driver is maybe 0 or maybe negative. It depends on how you're driving and what is your noise immunity of the system. There is no hard rule that you must apply minus 3 volt, minus 1 volt. Is completely depend on your application and how much negative voltage it can support. This buffer can be support. Generally it can be a minus 5 also. So for simplicity, I am assuming it is 0, because 0 is also a 0 voltage is also a common drive from 0 to VDD, 0 to 20 volt. So now at first instant, the 0 voltage is try to rise to 20 volt, right? So it is going slowly 20 volt. When it reaches the threshold voltage of the MOSFET, that is VTH, which is in the range of 1 to 2 volt, like that. So now when, okay, so so the current is charging these two capacitor, VGS and VGD. These two capacitor is the input capacitor seen by the gate driver. So it is charging these two capacitor. When this VGS is charged to 1 volt, then it caused the threshold voltage of the MOSFET. Now when it reached the threshold voltage, now your drain to, there is a channel formed between drain to source. The channel just start to form, and the time taken at this T0 to T1, which is at the first instant, or you can say from low to reach the threshold voltage, is called the propagation delay of your total gate driver or your total system of this system. So now the voltage across your gate driver is reached to the threshold voltage. Now, when it reaches to the threshold voltage, the drain to the drain to source, there is no longer a high impedance. The impedance, it can see a certain resistance, which is uh, called junction resistance or and uh, drift resistance of the due to the mobility of the electron. It just try to move. You can think like that. When you just try to shift this lever from this position to from off position to on position, when you just touch this pole, so this is just crossing the threshold. Okay. Now, when it crossed the threshold, the drain current try to flow from drain to source, but this is very minimum current because this channel is just on. It is not yet reached at RDS on value. So your drain to source is not enhanced at all. This is just from a, and when this replaced by the resistance, your CDS or the output capacitor is shorted by a resistance because this channel is on. So this now one capacitor is completely eliminated from this MOSFET. Okay, and now when this is the drain current try to flow, but this channel resistance is very high. So I square R loss will be very high because R is very high. So this is the most, this region is most lossy region because MOSFET is not fully on and you are trying to pumping the current from it. So due to that, a thermal runaway can be occurred because of high RDS, and body diode is just preparing to conduct. Now the gate voltage is further rise from threshold voltage to Miller plateau voltage. When it at zone 3, when it reached the Miller plateau voltage, when the full load current try to flow, but still the gate RDS is not fully turned on. So at the plateau region, because this current is flowing, so body diodes will start to conduct. So now when your body diodes start to conduct, the voltage drop across the VDS try to fall from high voltage to zero, or not zero, low voltage, because the voltage across the device is conducted by the body diode, is controlled by the body diode only. Body diode is conducting now, and also channel is forming. So now you can see the MOSFET is on, is turned on, but the RDS is not fully on. RDS is still dominating the channel resistance. It is still depending on the channel resistance. So now to avoid that, I need to pump a high current so that the gate capacitance immediately charge from the plateau voltage to the maximum VDD or the maximum biasing voltage of my gate driver. So at that region, I need to pump a high current. So this is some intelligent gate driver have to pump the high current. I need to reduce this gate resistance, R gate, right? This is the this is in my hand because this is out of the device. Rest of the resistance is not is inside the device, which I cannot be controlled. So some intelligent driver reduce the RDS on, R gate to pump the high current to the CGS, and CGS is immediately charged from 8 volt to almost the 18 volt or 20 volt like that. So now when you charge a and that driving current is the specification of peak driving current capability of the gate driver. If you choose any gate driver, you may see there is one parameter called peak driving capability, which is around 4 amp, 5 amp. So from that is that driving capability comes in this picture. So now when you pump the voltage, pump the current to the capacitor and charge the voltage from Miller plate to VDD, so the MOSFET is fully enhanced, and the channel resistance is now RDS1, and voltage drop across the MOSFET or VDS is ID times RDS1. This is the complete mechanism of turning on a MOSFET. So when you are designing a gate driver, you need to consider this kind of phenomena. You must consider this kind of phenomena. Okay, so now you see this is the VGS profile, practical VGS profile, which is taken at the oscilloscope. This is the plateau region, and this is the from plateau region to going to maximum VDS. And okay, the voltage across the device, when you turn on the device, the voltage across the device going from high to low, and current is going from low to high. So the cross section of these two profile is called switching loss. Here, this is the most lossy region, region 2 and region 3, because there that is called the switching loss. The switching loss happen at this two region when the drive voltage is passing from threshold to Miller plateau and Miller plateau to directly to VDD. Okay, so now how much power you need, or what will be your power supply capability to drive a MOSFET? That depend on this V drive, total V drive. If you consider the minus, then say 20 volt minus 5 volt, that which is total is 25 volt, into how much gate charge and what is your switching frequency. So this is your power rating of your power supply connected to the secondary side of the gate driver. Okay, so now how much current you can inject to turn on the to charge this gate or to turn on the MOSFET? How much current you can inject? That depend on there is the QG is the gate charge, which is specified in the data sheet, and T rise is the rise time of the MOSFET. Oh, yeah. So this rise time is depend on what is their internal channel. So how fast it is going from this drift to this channel. The impedance is from drift to channel. That is called T rise. So similarly, when you turn off the gate, you need to evacuate or you need to just swipe off all the charge from the gate so that it can quickly turn off. So this, so how the channel is formed, that is also another specification. These two specification you can find in the data sheet of every MOSFET. If you take any MOSFET, you can find QG and T rise, QG and T fall at any MOSFET. So from there you can design how much current you need to turn on the gate and how much current you need to turn off the gate. So from there you can design this RH or this resistance R gate to turn on resistance, and this is turn off resistance. Okay. Now here you can see this is a single buffer. Okay. So this IG on is the source current. Okay. This IG on is the source current sourcing from the buffer, and IG off is the sink current which is sinking towards the buffer. So now this is a single buffer. How do you control different current, which is source current and sink current? Because there is a single path. This resistance is single path. For that, there is one scheme called this is called steering control scheme. When you turn on the gate, you need to turn on slowly through RH or to high sink current, sorry, source current. Now, when you turn off the gate RL, that is sink path. You see, there is source path, this is sink path. So when you turn on the gate, this RL path is disabled. This diode is blocking the voltage. This is called steering control. So when okay, why we need to do this thing? Means why we need to different turn on and turn off. So when you see this is typical half bridge configuration. So when low side MOSFET is turned off, high side MOSFET should turn on, and vice versa, right? So there is a certain time when both are try to conduct. This is called a shoot through. So there is a shoot through current when you use the same source and sink current to the MOSFET. You can eliminate this shoot through by adjusting a dead time, but when you give a adequate dead time, means if you increase the dead time, your modulation you will lose the modulation, because the dead time is just freewheeling time between top switch and bottom switch. So just to avoid this thing, we need the turn on current should be slow and turn off current should be fast. That means this RL should be sufficient slow compared to RL should be sufficiently low compared to RH. Your pumping current is slow, but your sinking current is very high. So now if you see, the area between the cross section is very less. So low shoot through, you can give this much dead time or slightly higher than this in your control. If you have any question, I am ready to address. Do you have any question, or should I continue further?
So this overshoot, how it is reducing, that is not very much clear because of ROH and RL. Here in the first case, there is a overshoot, have a high value, and it is reducing. That is not very much clear there, sir. Again, please,
Which
can
one,
you
please?
explain it? In the first
Which one?
figure, that overshoot is there. In your shoot thought is greater. And the case of second, when you have added RL,
Okay.
when you have added RL
Okay.
in a parallel circuit.
When
So how it is
okay, when I add
reduces?
the
That is
RL,
not very much clear. Yes, sir. It is
so
not very much clear to
when
me.
you read when okay, when
Parallel
you
path you
introduce
have
this
added.
RL,
Yeah, with
okay, so
diode.
what is the effective, okay, what is the effective resistance
Overshoot.
at this network?
Shoot. Yeah.
No, what is
Suppose
the
ROA is
effective
high.
resistance? This is so RH parallel to RL, right?
Yeah. Right.
When you turn off, when you turn off, so turn off
Okay.
impedance is RL parallel to RH. Now RL is
Yeah.
much lower than RH. So RH is not dominating compared to RL. So the maximum current will be flow through the RL.
Yeah. Right.
Okay.
Yes.
Now
Yes.
when maximum current is flowing through RL, that means your gate capacitance CGS will quickly
Sir, one thing
discharge.
I want to know. This diode is forward biased when the voltage across gate is more, na? When capacitor is fully charged. VGS is fully
Okay.
charged. Then
Hmm.
this diode will be on. This
But your
diode.
this V out, the CGS cannot be greater than V out, right?
Yeah, then diode is only when VGS is greater, then only diode is on.
But how VGS will be greater than this source V out?
Then which condition this diode will be on?
Okay, the diode will be on when V out is 0 and VGS there is certain voltage during discharging condition when you try to discharge this VGS.
Yeah, right, sir.
So initially this V out is 0 to say 20 volt. So now your gate is 20 volt. The gate voltage is from 0 to 20 volt and the pumping path is RH only.
Yes. Got
Right?
it, sir.
Hmm. Now, when you discharge the VGS, V out is 0. So it is trying to follow the RL path.
Right, sir. Got it.
Okay. Hmm. So now this is fast. You are turning off very fast. Now see, there is this is the conventional gate drive. That one you may see in the lab. So here, see, this is the the both transition is similar, but here you see the both transition is different, and the cross section between this transition is shoot through current. Shoot through current means when your both bus is shorted through a resistance or anything, means your both switches are conducting for certain time, for very small time. So now you see the shoot through current is very less. Is it clear?
Yes, sir. Right now.
Okay.
Okay, sir.
No. Okay. So now this is the scheme where you can see I can with a small signal transistor, I can switch the turn on resistance with CPLD. This is one kind of research going on for intelligently drive the gate. So when I drive it with 1 ohm resistance, 1 ohm resistance means your what is the voltage, that is the current. Means if there is 10 volt, that means 10 ampere current is flowing maximum. So if you see, there is too much oscillation across the VDS, and the dV by dt is 64 volt per nanosecond. Now when you reduce the resistance, say at ohm, you see there is very slow transition and less oscillation. So which one is desirable? Obviously the low oscillation is desirable. So this amplitude of oscillation is depending on the circuit parasitics, what is the oscillation frequency and all that. I will come to that later. But based on that, you need to choose how much current you can pump to the gate, or how much current you need to turn on the MOSFET. This is very much important parameter. You cannot abruptly select any kind of resistance. Okay, nowadays this is one direction of research where with very fast CPLD they are adjusting this turn on current, so that you can see this kind of fast peak but very slowly stabilization. Like after plateau region, you need to pump the current. So from this connecting the parallel resistance, you can actively control the pumping of the current. Okay. Now there is another concept called Miller effect or Miller clamping. When you choose a gate driver, for some advanced gate driver, you may encounter this Miller compensation feature. Okay, so what is that Miller compensation? So when you turn off the gate, still when you turn off the gate is not immediately turned off. A drain current still flowing from the drain to source, right? Okay, so now this drain current component, one is flowing from the channel and slowly reducing from the channel, because MOSFET is trying to going into high impedance state. So during that time, since it is a pulse current, this is not okay. So when you going to transition the current, so there is an DIDT, because you are changing the amplitude of the current. So DIDT will affect these two capacitor, input capacitor. So when a small amount of current is flowing through GD and GS, as it is a very small capacitor, the capacitor will try to charge immediately. And when this GS cross the threshold voltage, which is around 1 to 2 volt, the MOSFET will again turn on. So when MOSFET is, but you are going to turn off the MOSFET, but MOSFET is abruptly turned on. You may see this kind of phenomena when you are doing experiment with high current. You will see when you turned off the MOSFET, the voltage across the drain to source, you will see very fast ringing and very fast turn on. That is because of this Miller effect. This is called the Miller effect. Now to reduce that, there is one scheme called Miller compensation. When the gate voltage is directly sensed and compared with the threshold voltage through a buffer. Now when you short the gate to source with another external small transistor or small FET, so the voltage across the gate will not going to threshold voltage. Before that, it will try to discharge. The capacitor VGS is discharged immediately through this VSSV. Now this is called the Miller compensation. This is very much important when you are dealing with high current, because when you are dealing with high current, ID is very high. So when ID is very high, the DIDT, the delta I at the numerator will affect this kind of will try to affect this phenomena. This is very much important when you try to design a gate driver. Okay, so now you see we start with a simple resistance, but to drive a MOSFET completely, actually you need four kind of signal wire from the gate driver. One is high side control, one is side control, one is clamp control, and another is from here to source, from source to the ground of the gate driver. Okay, so if you have very low cost application, then this is one very cheap solution, very low cost solution to drive both the gate and the both the high side MOSFET. So for low side MOSFET, we don't need any kind of isolation or any kind of sophisticated drive. From controller, you can directly pass through the signal to the buffer and just connect to the resistance, and you can drive the lower MOSFET. There is to drive the lower MOSFET is very much easy. Okay, and this is with respect to the ground. The controller ground is also can be this ground. Okay, now come to the higher MOSFET. So voltage across this node is unknown, right? You don't know this voltage because it is pulsating voltage, constantly zero and constantly between V bus and ground. So now when you try to activate this gate, you have to give a signal with respect to this source, right? So you need to apply a voltage which is greater than this voltage VGS. You have to cross the threshold more than this VGS. Now to do that, this is called a bootstrapping mechanism. You connect a capacitor to the driving source, and instead of connecting the another leg of the capacitor to ground, you are just connecting the capacitor to this floating node or this switching node. So if this voltage across the switching node is X, so now your capacitor is charged to drive voltage plus X, right? So when this capacitor voltage is high, automatically this capacitor is boost up to this node voltage plus drive voltage. Now when the lower MOSFET is on, see this capacitor is directly discharged to the ground. So like that, dynamically the capacitor is charged between this V bus and this ground node. And this is very famous method for low cost application. Okay, so how this timing control affect the harmonic noise across the switching node, or if you this is just an example of, okay, when you do if you consider any kind of power converter, there is in any kind of power converter, the switching node is switching between 0 to V bus, right? You cannot avoid that. You have to do it because this is switching mode power supply. Now when you switching between 0 to V bus, what is the harmonic spectrum happening across the V bus, and how this harmonic spectrum affecting the EMI performance? So now this is your gate control that can how slowly you are going from 0 to V bus, and how slowly you are coming back from V bus to again 0. This DVDT, how you are adjusting the DVTT. That is fully timing control. This timing control is done through gate register of the driving signal. Okay, so what is the effect actor harmonics? So you can see if I assume the both are same timing, so this create a low pass filter with first 20 dB attenuation and then 40 dB attenuation. This switching action can create a low pass filter. Now if you adjust this TR through this gate control, now the TR will move to the low cutoff of the filter will be automatically go further low. So your system will be then, if you see the EMI, if you see the FFT of your signal there, you can see some of the high frequency noise will automatically eliminated when you tuning this timing control, when you tune the timing through the gate register. This is very much important things in the, and if you tune this, your filter requirement is very low. Means you can have a small filter, small EMI filter to attenuate the switching noise. And this is very much important parameter when you are designing any product. This EMI aspect is very much important. Okay, now see, this is the, if you open a MOSFET plastic, this is the die of the MOSFET, and this is the actual MOSFET, and this die is connected through a bond wire to these terminals. So when a high current is flowing from drain to source, DIDT, so this bond wire inductance also dominating to your performance. So this bond wire inductance and this lead inductance also coming into the picture, that you cannot avoid. MOSFET, when you connect to the gate signal, you cannot connect directly across the source. There is some bond wire and lead inductance. So when current is switching, so DIDT effect is happening across this bond wire. So the inductance L into DIDT, this much voltage will appear across this bond wire inductance. So your overall drive is now reduced to drive minus this bond wire, this LDIDT. To reduce that, the Kelvin connection, where the source is directly connected to the inside of the die, and so the source connection is taken from that die. So using this scheme, this is called Kelvin source effect. Using this scheme, you can eliminate you can have a better control of the gate timing, and you can eliminate the bond wire resistance and the lead effect of lead resistance across your drive. Okay, so now when you connect your source, there is some wire or some PCB trace or anything, you cannot connect directly to so you cannot connect the source directly across your bridge. This is your bridge. You have to connect in a cable or anything. So when high current is flowing, those cable inductance also come into picture. That is called bus inductance. Because of the bus inductance, you are expecting your transition should be smooth from 0 to V in. Instead of that, you may see a lot of ringing. This ringing is depend on this bus inductance and this bond wire inductance and lead inductance as well. All the lumped inductance is coming into picture and oscillating with this this body capacitor, the parasitic capacitor, and create this ringing. Okay, so now how to reduce this ringing? This ringing cannot be eliminated. This ringing can be eliminated, but for a hard switching converter, this ringing cannot be eliminated, but you can control the amplitude of the ringing. So for that, if you use you can use first of all a snubber capacitor. So so high current will provide from this capacitor instead of bus for the transition. This the transition current is provided through this snubber capacitor. And also there is one method called bus bar architecture method, or bus bar. You can form a bus bar so that your plus and minus this bus will come closer, and this bus inductance will get smaller and smaller. That is done in the when automotive tractor and automotive converter, when you are designing the automotive converter, this bus bar structure must be done. Okay, so this is the Kelvin source MOSFET, where this input signal or drive signal is directly connected to the source. That can eliminate this high current bond inductance and this lead inductance. Okay. So now nowadays, because of advanced CMOS technology and all these things, the protection circuit is also included in the gate driver. So what kind of protection is required while you are driving the gate? So there must be two conditions for a switch, whether it is turn on and turn off. So when it is turn on, there is three different protection. That is called DSAT protection. And okay, when there is short circuit and you turning on the MOSFET, there is a huge amount of current flowing through the MOSFET, right? The short circuit current. Now there is called DSAT protection to sense how much current, not how much, to sense the threshold amount of current is the current passing through the device is crossing its threshold or not. When you sense this is passing the threshold, you can turn off the device immediately so that it can isolate from the short circuit condition. So there are three ways. One is DSAT protection. One is you can sense the current to a shunt across the source to the ground, and you can also sense VDS, because VDS is just an resistance. When it is turned on, VDS is resistance. If more current will flow, the voltage across the VDS will going to be increased. Now when you turn off the MOSFET, in the previous slide you see, when you turn off the MOSFET, bus will try to overshoot. Now when the value of this overshoot crosses the VDS rating of the MOSFET, the MOSFET will immediately going to break down, and that is called avalanche breakdown. So you immediately going to break down and you cannot recover from this breakdown. So that is happen only on off condition. So turning on the MOSFET is very easy, but the complication arises when you turning off the MOSFET. So to do that, to encounter this problem, there is called active clamping, and another active clamping. And another scenario may happen, but this is very rare scenario, when your MOSFET is floating but still drawing some current. This is very rare, but it may happen. So in that condition, you need to sense the get current, IG, that whether you are pumping any current or not, then why MOSFET is getting on. All this thing nowadays, because of building this artificial intelligence and all this thing, this can be, all this kind of protection can be incorporated to better reliability of the converter. Okay, now coming to the DSAT protection. So this DSAT protection is very much useful for IGBT device. This is not that much useful in when you are dealing with MOSFET. So for IGBT, when you are pushing the IGBT to the saturation region, now when you try to increase the current, drain the collector current, so that VC drop will be a fixed for that current. But when you try to take more amount of current, so the VCE voltage across the device is try to go up, try to increase. That is and the device is no longer be at saturation. It is trying to try to grow from the saturation point. So that is the abnormal condition. That may be because of the temperature effect and because of the short circuit condition or overload operation, the huge amount of current can be flow from the device, right? This is not the normal condition. So at that scenario, you need to sense the voltage, and you have to compare, you have to check the voltage whether it is going to a certain value or not. Generally, it is around 5 volt to 7 volt. When you if you see the Skyper 32 gate driver, which is made of semicron, to drive the IGBT, those block IGBT, this kind of protection is included in that Skyper board. So this is the blocking diode when to block the bus voltage, and when it is turned on, this one small amount of current is flowing to just to turn on the device, turn on this diode and check the voltage across the device. And there is one RC filter that is called blanking time adjustment, that to avoid the false triggering. This is very much useful in case of IGBT, not in case of MOSFET, because MOSFET is just a resistance, not the channel, not the saturation device. But it is very easy to implement, but there is very possible of false triggering. To avoid that, this RC filter is there. For MOSFET, this kind of scheme is implemented by sensing this resistance or sensing VDS. So, turn off the MOSFET, the bus will overshoot. So now, when the bus will overshoot, if you turn on the MOSFET in linear region, not in the hard, not in the saturation region. If you turn on the MOSFET slowly, then this bus will again slow down. Again, the bus will again clamp to the voltage, right? So this is another scheme when the voltage across the device is sensed and monitored, and when it shows that there is one blocking diode or blocking TVS diode. When this TVS diode turn on because of this overshoot, then it can sense there is something wrong and it slowly turn on the gate around just across the threshold region, VTH, between VTH to V Miller plateau region. Lesser than the Miller plateau, greater than the VTH. Slowly turn on in the linear region, so that the bus is clamped to again be clamped. This is called active clamping. Now there is another thing is that it can sense the how much current is flowing through the clamping through this through the clamping current. How much? This is another called advanced active clamping. This is another protection really used in automotive industry. So this is path when there is some overshoot. This TVS diode will this TVS chain will getting fired and turned on, and slowly charge the gate, as well as it can measure how current is flowing. So that voltage is also sensed, and also there is this current can be also controlled. Okay. Now how do you there is a famous test called double pulse test. Now how do you tune the parameter of the device, means at what current level it should act? How do you adjust this? For that, a double pulse test you need to do before tune the your MOSFET driver. So what happens is that for a single, when you do the single pulse, when this is your device under test, when you turn on the device, this L1 is going to charge. Now when you turn off the device, so this current is freewheeling through the diode. Now again, when suppose the amplitude of this current is around 20 ampere now, and you tuned your gate drive current limit to around 25 ampere. So now when you turn on the gate again, so this freewheeling current again try to flow through the device. So now when it trying to flow through the device, you can adjust your threshold voltage, that from here I will not allow this current to flow through the device, and your protection will act immediately. So whatever you give the input from your or your microcontroller, the gate drive will not give the pulse to the gate. That is called double pulse. This is very famous test. This is just a demonstration of some gate driver that I have made during my PhD. So this is very small. This is automotive grade gate driver. All kind of protection that I have discussed is implemented here. This is the TVS diode chain you can see, and this is the isolated isolated power supply for each channel. This is for full bridge, dual active bridge I have designed, and this is the main. This is bus bar architecture kind of thing I have designed inside PCB, so that the overshoot is very much less. Thank you very much. If you have any question, you may please.
Sir, thank you very much, sir. Actually, it is a very informative presentation. Sir, could you highlight on the bus bar design also for when you use this simulation software, which could be like more we need to practical oriented one like a PSIM or a T-space, which is suitable for understanding.
For busbar design, you cannot use PSIM because PSIM is doing the steady state analysis actually. The busbar is actually a transient analysis. For that, you need some finite element method software like ANSYS and COMSOL like that. And that is another domain of research or domain of development. That busbar design is not too much easy. Means how much gap you need to provide, what kind of material you need to give between the plus and minus bus. All these things have different field of research.